The second property that we are going to discuss now is shifting property. So property number 2, shifting property. Okay, and this is also called time shifting property. Time shifting property. We also had a similar property for Laplace transforms. So let us look at the time shifting property for Fourier transforms. Okay, so if the Fourier transform of the function small f of t is given by capital F omega, and we have another constant called t0, t naught, which is a real number. Okay, t0 belonging to the set of reals means t0 is a real number. Then the Fourier transform of the function f of t minus t0, this is equal to e to the power minus I omega t0, the Fourier transform of f, small f of t. This. Okay, let us prove it. So let us take the Fourier transform of f of t minus t0. And this is by definition 1 by root 2 pi integration from minus infinity to plus infinity f of t minus t0 e to the power minus I omega t dt. Okay, now let us change the integration variable from t to some tau. So let us define a new variable tau as t minus t naught. Then t becomes tau plus t. I repeat, t becomes okay, tau equal to t minus t naught. Then t becomes tau plus t naught, and dt, this dt is equal to d tau, because there is no scaling. We are only shifting the origin. Then in such a case, this Fourier transform becomes, it becomes 1 by root over twice pi integration f of t minus t naught now becomes f of tau e to the power minus I omega. Now t becomes tau plus t naught. This becomes tau plus t naught. Integration dt is, it becomes d tau. Now let us look at the limits. This tau is a real number, which is a constant. It's a finite number. Okay. So when t is equal to minus infinity, from minus infinity, if you subtract any finite number, the answer is still minus infinity. So it becomes minus infinity. So tau is minus infinity when t is minus infinity. Now let us look at the upper limit. Okay. Here, the upper limit when t becomes infinity. So when t becomes infinity, tau is a finite number. So if you subtract from infinity any finite number, the answer is still infinity. So this is infinity. Okay, this is clear. So far, so good. Okay. This is equal to, now this t0, it is a constant. So e to the power minus I omega t0, it is a constant. It can be taken outside the integral sign. So e to the power minus I omega t0, it's a constant. It's taken outside the integral sign. Then we have minus infinity to plus infinity f of tau e to the power minus I omega tau d tau. Okay. So, and what is this? This is nothing but the Fourier transform of the function f of tau. Okay. Then this is e to the power minus I omega t naught, the Fourier transform of the function f, and this we represent by capital F omega, which we have written here. So we have proved this property, hence proved. Okay. Now let us look at one application of this property. In today's class, we shall discuss two more applications of this property and then we shall stop. So let me take a new sheet of paper. So example 1 again. Find the inverse Fourier transform of the given function. E to the power I omega minus I omega 1 plus I omega. So if you look at the shifting property carefully, this is the shifting property. If you look at the shifting property carefully, here we have e to the power minus I omega t0. Here we have e to the power minus I omega times 1. So if you compare this and this, we find that t0 is equal to 1. So here t0 is equal to 1. And this is e to the power minus I omega t0 times the Fourier transform. So if I remove this, what remains is 1 by 1 plus I omega. So f of omega is 1 by 1 plus I omega. Okay. Then, therefore, if I take the inverse Fourier transform of this e to the power minus I omega 1 plus I omega, from this you can see that if I take the inverse Fourier transform of both sides, that is inverse Fourier transform of the Fourier transform will give the function itself. So this we shall get f of t minus 1, where where f of t is equal to the inverse Fourier transform of this. Okay, inverse Fourier transform of f of omega, and what is that? That is the inverse Fourier transform of 1 divided by 1 plus I omega. Okay, and then from one of the examples that we saw, and then from one of the examples which we discussed earlier, this e to the power minus at ut, we had obtained this result, 1 by the Fourier transform of e to the power minus at ut equal to 1 by root 2 pi 1 by a plus I omega. Okay, so this is 1 by 1 plus I omega. So here it is a is 1. Okay, so we are going to use this result. Okay, we are going to use this result. So we know that Fourier transform of e to the power minus at u of t, this is equal to 1 by root 2 pi 1 by a plus I omega. This was the result which I just showed. Okay, so this is what we have. If you compare this and this, we find that a is equal to 1. So if I bring 1 by root 2 pi towards the left, it becomes 2 pi. Or if I take the inverse Fourier transform of both sides, what do you have? What do we get? If I take the inverse Fourier transforms of both sides, what do we get? We get inverse Fourier transform of 1 by root 2 pi 1 by a plus I omega. This is e to the power minus at u of t. Okay. Now, if this 1 by root 2 pi, this is a constant, and from the linearity property of Fourier transforms, we can take it outside. Okay, I forgot to mention that the inverse Fourier transform also satisfies the same linearity condition. Okay, the inverse Fourier transform also satisfies the same linearity condition which the Fourier transform satisfies. So this is a constant, it can be taken outside. Okay, so now you compare this and this. You compare this and this, what do we get? Therefore, 1 by root over twice pi Fourier transform of, if I put a equal to 1, I get this. 1 by 1 plus omega. This would be equal to e to the power. Now I have put a equal to 1, so e to the power minus t u of t. Okay. Now I bring this towards the other side. So this implies Fourier transform of 1 by 1 plus omega. This is equal to root over twice pi times e to the power minus t u of t, and this is equal to f of t. Okay, because we have defined f of t as the inverse Fourier transform of this, and the inverse Fourier transform of this is equal to this. Okay, therefore, what remains is only to shift the value of t from t to t minus 1 because of the presence of the numerator term. So we finally get, therefore, inverse Fourier transform of e to the power minus I omega 1 plus I omega. This is equal to f of t minus 1. Now, if I put t equal to t minus 1, so if I replace t by t minus 1 in each of these terms, what do we get? This is equal to root over twice pi e to the power minus t by t minus 1. We have replaced t by t minus 1 multiplied by u of t minus 1. So this is the final answer. Okay, so we have simply applied the shifting property. Now let us look at the last example for today. Last example for today. Okay. This is again an application of the shifting property. Example number 2. Find the inverse Fourier transform of the function 4 times e to the power minus 2 I omega divided by 4 plus omega square. Now look at the shifting property again. Here we compare this and this. So e to the power minus I omega t naught. This is e to the power minus twice I omega. So t naught is equal to 2. So here t naught is equal to 2, and the Fourier transform that is equal to, what remains after removing this term is simply 4 divided by 4 plus omega square. Okay, therefore the inverse Fourier transform of 4 times e to the power minus twice I omega divided by 4 plus omega square. This is equal to f of t minus 2 where f of t is the inverse Fourier transform of the remaining terms. It's the inverse Fourier transform of 4 divided by 4 plus omega square. That is the inverse Fourier transform of capital F omega. Okay, so let me remove this paper. So first, let us calculate the inverse Fourier transform of this. And from an earlier example which we solved, we know that the inverse Fourier, the Fourier transform of e to the power minus a modulus of t. This was the first example which we solved. This was equal to root over 2 by pi a divided by a square plus omega square, where a is greater than 0. This was the result which we obtained earlier. So you compare this and this. You compare this. So we have a square equal to 4. So 4 plus omega square should be equal to a square plus omega square. That means here a is equal to 2. So a is equal to 2 means this is 2 square plus omega square, and this is twice a, 2 times 2. So this is twice a, and I can take 2 outside. Okay, so therefore the inverse Fourier transform of 4 divided by 4 plus omega square, this I can write as inverse Fourier transform of this denominator. I can write as 2 square plus omega square by comparing with this form. So 2 square plus omega square, and what should we have in the numerator? Numerator we should have a. So we have 4 here. We need only 2 here. That means we take another 2 outside. So this 4 is 2 times 2. I have taken 1 2 outside. Okay. Now this is equal to twice. What is the inverse Fourier transform of this? Because from this expression, we see that the inverse Fourier transform of this would be equal to, this will come towards the left, like pi by 2. This 2 by root over 2 by pi will become pi by 2, and this will be e to the power minus a times modulus of t. What is a here? A here is equal to 2. So this will be e to the power minus 2 times modulus of t. And this is equal to, if I simplify it further, I repeat, if I simplify it further, this should be equal to twice pi e to the power root over twice pi e to the power minus 2 modulus of t. And this is f of t. So the final answer would be f of t minus 2. Therefore, inverse Fourier transform of 4 times e to the power minus twice I omega divided by 4 plus omega square. This is equal to f of t minus 2, and this is equal to, if I put t equal to t minus 2 here, we should get root over twice pi e to the power minus 2 t minus 2. So this is the final answer which we have. Okay, so let me stop the recording here.